Well, hello there. Alright, so today I figured we'd take apart a Morimoto XSB LED halo. It's one of the switchback halo models. So obviously it has white as well as amber LEDs on the board here. We'll see what we can learn. And yeah, see how this driver works, and maybe even after understanding what we can learn here based on the array of chips and how they're wired on this halo, we can kind of learn how to make our own halos. Alright, so we took apart this Morimoto XSB LED driver. It looks very similar to, a handful of other drivers we've been playing with. As far as components, it looks like you have capacitor still. Not even really sure what this, wound up wire is, but I'll look into that later and learn something. But yeah, very similar. I mean, even the size of the board is pretty similar. So let's understand how this works. So it looks like we have, as I'm sure everyone knows with the Morimoto switchback halo products, we have a ground wire, which I've hooked up to ground. We have a white wire, which is positive for the white chips, and then we have an orange wire, which is positive for the amber chips. So let's look at the chips first, I guess, right? We have basically 63 individual chips on this PCB board. And it looks like there's two chips or two diodes inside each chip, right? So we have a white and an amber. So knowing that, why don't we wire this up and see what the driver is outputting and such, so we can get a sense of current consumption and whatnot. Alright, so if we hook up power to the 12 volts, we can see that the white chips are being ran and driven at 325 milliamps. So as I fluctuate the power source from 12.5 to 15 volts, you can see the current stays the same. So it's a constant current driver, right? We learned about those in the previous video. It's a efficient way to drive LEDs. Another thing to take note is the voltage basically drops to 8.6 volts when these LEDs are being supplied with power. So we'll write that down. Let's check out what the amber does. Alright, so the amber chips, the voltage drops a little bit lower, 6.1 volts, but they're still being driven at the same amperage. So we'll jot that down as well, and we'll do some math here and see if we can figure out how these chips are wired. Based on the number so far, I'm going to guess three sets of three would be my assumption. So why don't we start by hooking this back up. Keep this here so we can monitor the voltage at all times. And what we'll do is see what happens when we take the meter and consume the current from one of these chips. My guess is a section of chips is going to go out. Right, so hopefully you guys can see that. It looks like a third of the chips went out, which will kind of align with my theory of three sets of three. Let's try a totally different chip on this side. So there, again, you have it, three sets. So let's count how many of those LEDs are actually going out. 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 21 chips. So we know that we have a total of 63 chips, so 21 times 3 would be our 63 chips. So it looks like they are wired in some fashion of 3 by 3. Let's check the voltage of a single chip to get some more numbers here. Apologize for the noise. Dog's running like a crazy animal upstairs. So let's check the voltage of one of these single chips. See what we get. 2 volts even. Check the voltage over here. Also 2 volts. Let's check the voltage from there. Say this side. Also 2 volts. So I think we've learned that they're wired in 3 sets of 3, it seems, right? So let me write some of this down, and then we'll check the white chips. Alright, so checking the white chips here. We intercept current. Obviously still going to be the same. I didn't expect, obviously, how they're wired to change. However, if we check the individual voltages, so let's check the total voltage when these are running at the driver. See what we got. 8.5, 8.47, so 8.5 volts. Alright. So if you remember, the amber chips were only pulling 6.1. So let's check an individual chip. White chip, to be specific. Come on. Two volts. Sorry, 2.8 volts. So the white chips are running at 2.8 volts. And the ambers were running at 2 volts. Which makes sense. White's always going to usually have a higher voltage than any other color. So knowing that, we should be able to do some calculations and be able to inject power to individual chips and have just one light up based on our math and assumptions here. We can also, should technically be able to dial down my power supply on the bench here and totally get rid of the driver if we wanted to put power to only the white chips or only the amber chips, and we'll test that theory out. I'm thinking I'm going to continue that in another video, though. This was really just kind of to quickly go over the driver and get some numbers. I don't really have too much time today, unfortunately, but maybe I'll continue doing those other things tomorrow and see what we can learn. Anyway, hopefully this helps someone somewhat understand about how these things work and what I've understood and figured out myself so far. I think it's pretty cool stuff. And then I think maybe next steps, and might be jumping ahead of myself here, right? But maybe what we'll do is I'll take a whole bunch of these 3528 chips. We have them in white and amber, and maybe what we'll do is try to, I don't think I'll do 63 chips. That'll take forever. I mean, I don't have PCB circuit boards that are ready for soldering these SMDs on or anything, so I'm gonna have to do it all by hand. But maybe what I'll do is we'll make our own ad hoc halo. We'll lay some chips out, and I'll use some wire and some solder, and we'll kind of wire a ghetto halo. Actually, you know what? Maybe we'll make something like a hex halo, kind of like an ad hoc hex halo. We have the drivers to do it. We have LEDs. Just got to make sure we facilitate the heat that they're going to generate. Kind of what this PCB board helps exhaust. And yeah, maybe we'll try to design our own custom little halo and see what happens. All right. Hopefully you guys are into this stuff, and I'll keep making the videos. Thanks.